So first of all, thank you, Dr. Srinivas, for setting the context around how much heat is being generated, especially for AI workloads. And you very much rightly pointed out how the peak load based design is a kind of an overkill. And what software also leads us to do is also manage what kind of new hardware can come, where both the software hardware can interface to really deliver and unlock a lot of abundance, which we call at Uravu as unlocking thermodynamics of abundance, especially around reusing this waste heat. Uh, so if you look the whole spectrum of data center cooling solutions today, you have at one end cooling towers, which consume a lot of water, almost 60 to 80,000 liters per day per megawatt. So very high water usage effectiveness, but have very low energy. So they're low on energy and low carbon, but very high amount of water. And on one end, you have air cooled chillers, where you can call yourself even going water less or water zero water, but then your PUE or energy consumption becomes very high. And again, you have to design for peak loads. That means your under capex, power distribution, everything becomes even more higher investment. And then somewhere in the middle, you have your hybrid kind of solution where you can use dry coolers for most of the time, use chillers only when you need it. And so today becomes, especially because of AI, your choice of cooling architecture is becoming a very strong balancing act between how do you manage both water, energy, as well as to a lot extent regulations today, right? So grid is a constraint, water is a constraint. So these are things which are important to manage. So we are kind of designing a very flexible software and hardware platform, which depending on your waste heat load, which is basically all IT load gets converted to waste heat. We are utilizing that to reduce cooling energy consumption while also producing water from air in the process. So the idea is data centers can actually convert to a low carbon and water positive infrastructure rather than being water guzzler and emitting carbon emissions. So that's the whole idea of in general what Uravu does. And we don't interfere anywhere at the server level. The idea is that whatever hot water gets carried through to the facility water and to the outside of the data center hall, mainly to a cooling tower chiller, we will intervene there and then reduce both the cooling and water side of the equation. And if you look at the two metrics which are most widely used in the industry, one is your PUE, power usage effectiveness, and other being WE, water usage effectiveness. With our solution, the idea is can you get both a very low PUE and we're introducing a new concept called as negative WE, because now your data center is not consuming any water but rather producing it and can give back. So how the solution works in our case is we use a proprietary liquid salt which absorbs moisture from ambient conditions as low as 20% humidity. We then let it pass through a chamber where this air and liquid salt interact. It absorbs the moisture. And then finally, we apply a heat which is coming from your facility water loops and then convert it to high quality water. Now, the idea is that because of AI heat loads increasing, you're getting much higher temperature heat. So while you're also not constrained by a 5 to 15 kilowatt server racks, now you have 150 plus kilowatt server racks, which are even going up to, in future designs, up to a megawatt is what the industry is moving forward to. So while your amount of heat intensity has increased, your heat temperature has also increased, which makes it viable for such use cases to emerge. And these are again, the way we look at it is that we don't have to intervene in a way that it changes anything, but all your return loops can be first interfaced with our hardware. And the beauty of the hardware is also it works around a flexible load architecture. Because at one side you have facility water, which is a liquid, and in our side, machine side, we also have a liquid salt. So it can, modulate its flow rate and heat rejection basis your variable load coming from the data center. And we monitor close to 25 plus parameters in real time including both your absorption of water, water production, flow rates, etc., to then give you a very high efficiency solution. And we have analyzed this, with all kinds of weathers and waste heat temperatures across more than 30 plus locations globally. And what we see that is, in most cases, we are able to show energy reduction from your existing cooling system by 10 to 16%, as well as make about 10 to 30,000 liters per day per megawatt of water, which is then used for cooling or given back to communities. There was this one case study I wanted to share, mainly for New Delhi as a location which is, very hot and dry, and has very high PUE. If you just say use air chillers, it will be almost 1.3, 1.4 kind of. And if you use a hybrid solution, we still see that even at 35, 40 degrees, it's still well above 1.2, 1.22. With our solution, we are able to, reduce that PUE from 1.2 to 1.14. So you have, good substantial saving there in your overall energy reduction as well as your overall load. And we also use, a lot of tools to analyze your overall peak load shaving. So as again, Dr. Srinivas was also telling that a lot of this design today is for peak load. But as you can see in this, overall, we see the baseline power is hardly utilized for peak loads for, hardly 20% of the time for a Delhi kind of place. For most of the time, it's, more than less 50, 60%. So you're designing for, extra for so many hours, which is not even needed. Whereas our solution is acting to, shave that peak load while also maintaining a more flexible and, performance throughout the year. So that leads to, more savings in cost, more savings in your reduction in DG sets, reduction in your power and distribution requirements. And roughly for a 100 megawatt data center in Delhi, we can save $7 to $10 million, just in initial capex, where we can, with our solution. And today we have a smaller unit, for plus peak load reductions, shaving some of the load, which is a 2000 of the 125 kilowatt. And we are also developing a 1 megawatt block, which will be ready by year end, which can be deployed for larger sites. So that's all from my side. I'm happy to engage and hear more from my fellow panelists on how they're going about solving the thermal challenges for the industry. Thank you.